Okay, so let's start our seminar. We'll now have a look at everything that was covered in the lecture, and we also will inspect the Hugging Face Transformers trainer, which is very suitable for training, for fine-tuning, for any types of training, and we'll see how we can modify it for our special purposes. Let's first start with some with the same material which was used on the last seminar. We make the same imports. By the way, as we discussed previously, we can load all these imports using this command. But yeah, the file with the seminar is on GitHub. You can open it, and it would be great if we write code together with you. So all the same cells here, and here was our training cycle with early stopping. Everyone remembers what early stopping is? Should be.
Stop training process
Yeah.
Does not decrease on the validation for 2 steps.
Yeah, great. So, but instead of writing these custom loops each time specifying the what we must do on the train stage, on the eval stage, we can use the pre-written trainers, which help us do all of these automatically and in a lot of more structured way. So the trainer from the Transformers library is ubiquitous in that sense that it can be applied to any task. We only need to specify the main components of the model training. So what it is? We import the class trainer here, and it needs to have several attributes. Wait, I'll find this cell. What we need to pass to this trainer? Basically, we need, first of all, the model which it will train. The model must meet only one requirement. Either we can do it like this, so we can inherit the class trainer and rewrite the method compute loss, or instead of this, we can do a bit easier thing. Instead of this, we can modify our model so that it returns a dictionary of values. Our model, after the forward pass, it must return a diction of 2 values, the loss and the logits. The logits will surely be returned both on train and on inference phases, and loss will only be returned on training phase. If we make such a class that after forward pass it returns the dictionary, we can even skip this step of inheriting from training and overwriting this class, and we will be able to use simply our train. That's it. Okay, in this implementation, we use absolutely custom model, but if our model does not return this dictionary, we need to change the compute loss method, which will define how the loss is computed, how the backpropagation goes. The next attribute of our custom trainer is the training args. So Hugging Face also provides the class named training arguments. There are a vast number of different values, some key values which usually need to be specified. This is the only required argument. Test trainer is the folder where the logs and the output of our trainer will be placed. Evaluation strategy, whether we want to evaluate our model after each epoch or after some predefined number of steps. Logging strategy should coincide with evaluation strategy and serves for the same purpose, how often to log our results. Seed, well, to fix the seed for training, for batch division for training step, to make the results reproducible. Learning rate, obvious. Weight decay, the parameter for, again, for Adam V optimizer, this weight decay, which is a kind of a L2 regularization, number of training epochs, or instead, if instead of using some predefined number of epochs, we want to use some predefined number of steps, number of gradient updates, we could use the parameter called max steps. If both of them are specified, this one is the leading one. So if both of them are specified, this one will be simply omitted by the model. Per device train batch size. The transformers trainer allows us naturally to parallelize the training for several GPUs. So if several GPUs are available and it sees that these GPUs are available, the training will be parallelized. And so this argument, it has some common name, like the number of batch size per each GPU. For CPU based machines, okay, that's just simply becomes your batch size. The same for evaluation. If we override this compute loss method, we also need to specify this very argument label names, which will tell us which key of the data set corresponds to our labels. Some other arguments which are not listed here. By the way, report 2 transformers very easily synchronize with a lot of different systems to monitor your model training process, like 1DB, like MLflow, etc. And if you want to look to any of them, you can specify, for instance, 1DB. That's it. Some other arguments which are not listed here. By the way, I do not remember that I covered this on the lectures. The gradient parameters are rescaled. That's it. That we have very large gradients, and we restrict their norm. We say the maximum norm of our parameter will be some predefined value. And if we see that the norm of our parameter has a larger value, we simply divide it by itself. If we have max gradient norm of 1, we need to divide it by itself. If we have it 2, we can divide by so multiply by 2. Hope you get the idea. So we can restrict the maximum norm of our parameters. And by default, here is a value which is called max grad norm, which also corresponds to this value very thing. By the way, I need to restart all the cells. Yeah, I think it was not launched this way. Okay. That's for the training arguments parameters. There are a lot of different parameters. They're like label smoothing for some special techniques. We will cover them a bit later. For now, let's use only these base parameters. The next thing which we need to specify for our trainer is the training dataset and the evaluation dataset. Last time we had an overview how to write our custom datasets, and they can be naturally used here. But instead, we can use the predefined, again, Hugging Face dataset from another library called datasets. We import the class dataset, and what we need to provide here is this simple structure. So this is our features matrix, this is our target variable vector, and we create a dict using the following syntaxes. So we create a dict with these two values, and we create the dataset from dict. Oops. I'm sorry, 1 second. Okay, so no questions up to now. Everything clear? Okay, so we specify both the train and the evaluation datasets, and the last obligatory part of our trainer is the compute metrics function. So our trainer needs to know which metrics to compute, how to compute them, etc. So we need to write the following function. Let's briefly discuss its syntaxes. So as an input, this function will be called inside the trainer, so you will not explicitly see how this function is called. It is done in the trainer itself. It accepts one argument of class eval prediction. That's the class of transformers, some inner class, which can be it possesses both the predictions and the true values. And to restore the predictions and the true values from this, we simply use let it be like a list. Yeah. So we write our custom compute metrics function, for instance, for our very case. Remember that we scaled our target value, and it's better done each time. We use the neural networks for tabular data. And to have a better overview of the metric value, it's better to restore its scale, since if we have these very low values like this, it does not tell us anything about the generalization capability of our model. So we need to restore this, and this can be naturally done in our compute metrics function. So we restore the scale of the target value, of the prediction values with respect to the target value, and we calculate the mean squared error. We can specify this argument squared false to make it RMSE. And here is our compute metrics. As for the syntaxes, it must output the dict with the values of the names of the metrics and what they contain. That's it. This class it can be either specified or not, depending on your preferences. Again, going back to the question from the lecture, if you want to use SGD here, you can specify SGD here, and you can provide this as an optimizer. But if we do not provide this very argument, we do it like this, it will be okay. The Adam V will be used as a default method under the hood. That's all regarding the custom trainer. If you have any questions, please. Okay, no questions. So, like what we do, we initialize our model, we put it to the device. If we want to specify optimizer and scheduler, we do it here. By the way, we spoke about optimizer, but as for scheduler, again, if we do not provide scheduler here for our optimizer, by default, it will use the triangular slanted learning rate scheduler. I'd better Google this to show you the picture. That's it. So that's the modifier of a learning rate. For some small number of iterations, it goes from 0 to large value, so that to prevent some very large values at the beginning of the training. And then throughout the rest number of iterations, it gradually goes again back to 0. So that's the slanted learning rate scheduler. And regarding this, yes, it was created specially for natural language processing. So I would not suggest you using this for other trees, be it a tabular data, be it for computer vision, speech recognition. But again, in most cases, it does not make much sense. So whether you use exponential learning rate decay or you use this one, it will not, the results will not differ significantly for these cases. That's it. So after we initialize the train, we train it using the like simple command train. That's it. Let's relaunch this cell together so that we'll see the progress. Need to relaunch this, and this. Yeah, so since our data set is too small, and for now I'm using the GPU for the training, you can see how fast it goes. So it outputs us a pleasant to look at data frame with training loss, validation loss, and our metrics. So if we had several keys here, they will all be listed in this data frame. And what we can see, for instance, that on fourth epoch, right, the quality on the validation slightly decreased. I guess this one is much more convenient to use than writing your custom loops. But again, when the application is like, I don't know, you have very specific tasks, you have to optimize in very specific way. Probably sometimes writing your custom loop will be easier, though I myself have not encountered such cases during my practice. That's it. We can evaluate our training on some other data set using just, again, one line, evaluate, and it gives us the results. That's it. So that's regarding the trainer and how it can alleviate our life for writing our custom loops. If you have any questions, let's discuss them. Okay, no questions. So let's move on and let's cover the layers which we spoke about during the lecture. The dropout, first of all, which zeros some of the neurons randomly during training. The first thing which I need to mention about the dropout is that for regression problems, it can sometimes lead to poorer results and will not prevent overfitting. So it was found that for regression tasks, like it was a research a couple of years ago, I guess about 2 years ago, where they took 8 regression data sets with tabular data and tried to use the dropout in the neural network. And they saw that depending on the dropout layer, zero dropout rate means just disabling the dropout, training without it. Yeah, we can see that for 5, I guess, data sets, the performance decreased. So that's an important notion about the dropout, that when applying to regression problems, be careful about using it or use some very small values at least. So how to adapt dropout in our network? So what we had previously was like a simple neural network. We had linear, ReLU, and the linear output. Yeah, let's rewrite this from scratch together now to better understand the syntax. So as usually, we have some input features to specify, some out features to specify. Hidden size can be either specified or sometimes it's like fixed inside our class. So how we did it last time? We used FC1 for first linear layer, we used FC2 for second linear layer, and again we can do like this here as well. But the problem is that it will give us a lot of attributes to store, and probably like some of you would prefer to call it FC1, like fully connected one. Another person will name it dense one. The second will name it linear one. And it will be hard to like understand which, I don't know, the conventional name. So when you have some very predefined structure of them and they are done, the operations are done sequentially, right? So each operation, like first of all linear layer, then the activation, then the dropout, then again the linear layer. When you have this in the predefined order, sometimes it's easier to wrap all of this in the so-called and then sequential class. Let's have a look at this. So and then sequential, what it does, it simply accepts the method, the torch layers here, which will be applied again sequentially to our data transformation. The only requirement to these layers, again, if you probably want to use some custom layers here, is that they must be inherited from an N module as this one, and they must have methods init and forward. That's it. So everything else Torch will do for you. Let's write our architecture. So the first one is as usually linear transformations, linear transformation of a data. So the in features is the number of features that goes into this layer, and the output features is the hidden size 1. Let's call it like this again. So after this, we simply like list the number of them. I'm sorry, list the layers which we want our sequential to consist of. Second, let it be ReLU activation. The next one, let it be the linear again. We'll have hidden size 1 as an input, hidden size 2 as the output, and then we apply the dropout layer. Oops, I'm sorry, first of all, we need again surely the ReLU and then the dropout according to the best practices. And the output, again, we need to have some linear transformation for our output. This will be hidden size 2 as the input and in features as the out features, I'm sorry, as the output. That's it. So we'll have all our structure wrapped in this and then sequential. And another benefit of it is that our forward pass will simply look like this, self-sequential, instead of like writing all of these layers and applying them to our input just in one line. That's it. Oops, yeah, I forgot to close the brackets. That's it. Another option of custom of Hugging Face trainer, which we'll use throughout. Yeah, sure.
And shouldn't we write a like self before each attribute of the class? I mean, hidden size self of
I see what you're speaking.
the attributes of the class.
Yeah, sure, thank you. Yeah, we can do it simply like this. We do not need to store this information. It can be easily restored from our layers if we need this. Again, a matter of preference. If you want, you can use it self hidden size and self everything here. Another option of the Hugging Face trainer is that sometimes it's when we like experiment with different architectures, it will take some time, like not some time, but some lines. We need to set the seed, we want to return the model, and we want to pass the model here. Instead, what we can do is just to fix seed if necessary and provide the model init function, which returns our model. And for our trainer, instead of, as we did it previously, like providing the model itself, yeah, the class of the model initialized, we can just provide the function for initializing the model. Most of all, this is used when optimizing the hyperparameters of the model. Again, later in the course, we'll see there is a decent method of this Hugging Face trainer called optimize hyperparameters, which allows us to use the modern methods for hyperparameters optimization, like parsing trees method, very easily, just in several lines of code. For everything. So like the hyperparameters can surely also be tuned. There are like modern algorithms, most of them are based on some Gaussian distributions, the thing for parsing model trees. And for these cases, of course, we need to reinitialize our model each time, each run with the hyperparameters. Again, for simple use, a matter of preference, you can use either model init or provide the model itself. Okay, so that's it. We reinitialized our model. So now it has the dropout layer. We have this. Okay, let's verify this, like the probability of zeroing a neuron is 20%. And we'll launch our training. What's interesting, if previously we could see the RMSE optimal was here, yeah, now it's a bit lower. That's it. So again, evaluate on some test data set. Again, this is the metric on some validation set, according to which we make the early stopping. And here are the metrics for test set. I don't know whether you were told on your previous courses or not, but a very popular mistake, which must be like, you should not do it this way. This set which was used for early stopping or for tuning the hyperparameters, it must not be the test set. It must not be the set where you assess the quality of your model. So the model performance should be evaluated on some set which was not used anywhere at all. If like it was present in early stopping, for instance, or for hyperparameters tuning, or even for scaling the parameters before feeding them into the neural network, the results will be biased. The biased results meaning that you may like incorrectly compare different models, and your final models may struggle to work well on some new data from the, I don't know, from the customer, like some other applications. So the idea is as follows: test set only for measuring the quality of our model. That's it. So that's our quality. Let's store it here. That's the RMSE on the test set. If no questions regarding the dropout, let's move on. So now the batch norm, and we'll do absolutely the same thing as we did this dropout, use the same architecture, just we'll apply the batch norm here for our data. By the way, batch norm is surely dependent on the size of our tensors, and if we're applying it to tabular data, it's applied to one-dimensional input, right? So like each feature is one value. So we use the batch norm 1z. If we use it for, let it be, we are using batch norm for texts, which are 3D tensors. We would use batch norm 2D here, surely. For computer vision, mostly we use batch norm 2D as well, to my mind. That's it. So reinitialize our architecture, and thanks to this very function, which we wrote here, modeling it, what it will do, it will find the defined class model in our notebook, right, and initialize the model correspondingly. So we can just not take care about any other like initialization of the model, just provide this very function. It will see that we reinitialized the class, and let's reapply it. So with batch norm, we find also a decent value, which was much larger, by the way, than the one we obtained on last seminar with using our custom training loop. And that's the performance on the test set. By the way, I think that it's slightly worse than with the dropout, but okay, this may happen. Okay, the next layer, like layer norm, absolutely the same. Instead of providing the batch norm here, let's provide the layer norm and see how much the performance changes. So on test set, we have some, I would not say that's a decent value. So the layer norm for this very case is not very much applicable. And that's it. But of course, the best practice is to combine the layers. And as I already said on the lecture, for tabular data, like batch norm is conventionally used. So we do the linear transformation, batch norm, activation rule for now, and the dropout layer. Let's see which performance we have using this architecture. And we use, well, interestingly, that's slightly worse than the one which we obtained with dropout. But ideally, we would use this combination of layers between each linear transformation. So not only after the second linear layer, but we can use it here as well. And we can probably increase the dropout layer. So doing it like this will probably lead us to some bad results. Oops, I'm sorry. It was not correct here. Interestingly, it did not. That's it. Okay, I'll restore the original architecture. By the way, one important and interesting notice about this. For computer vision neural networks, batch norm is applied almost after each linear layer, at least at the feature extraction part. We'll speak about this on the next lecture, but like we'll mostly encounter applying the batch norm after the linear transformation, the same for tabular data. What is interesting, that this is linear transformation, this is like on training, it calculates the statistics on the batch. Of course, this is a bit different transformation, but on the test set, on the inference set, the batch norm statistics, they become fixed. So we have like a calculated during training mean, calculated during training standard deviation for each parameter, and then we have a linear transformation. So during inference phase, this the batch norm layer becomes a simple linear layer, and that's the idea. So when applying the inference for this network, we can simply, how to say, concatenate these two layers in one, since the combination of linear transformations is simply a linear transformation. So when applying batch norm after linear, and if you need to accelerate the performance of your model, you can simply combine these two layers, you can simply concatenate them, and it will lead us to absolutely the same results, since the combination of linear layers is another linear layer. And according to the observations of the paper where this method was suggested, it could accelerate some modern architectures up to 30%, without doing almost anything, without any decrease in the performance. Just using the simple method here, we can accelerate up to 30%. That's an interesting idea, which you should keep in mind when working with batch node. Okay, so just a decent data frame with the results of different methods, which show us that using them, well, it's a bit strange that we had some better performance with combination of the layers, but frankly speaking, we used only 5 chaining epochs for this model, and probably it needs some more to converge. That's all right, but the most important thing which we can see is that it has much better test RMSE than the raw model. So such special layers will surely enhance the quality of your model. If there are any questions how to incorporate these layers into your model, please feel free to ask. If not, okay, so now we'll see the techniques of initialization. So first of all, how should we initialize the layers in Torch with some values? So we'll use such a function. So what it has, what it accepts, that's the module. This is just the Torch model, either, and then like any layer of your neural network. What it does, it checks whether this module is a linear transformation. If it is, then we need to initialize the weights correspondingly, right? So if this is a linear layer, then we need to apply our init function to initialize the weight. For the biases, if we use some predefined values like with zeros, with ones, initialize with this very value. If we use otherwise, we would use some small value for initializing the biases. By the way, in the majority of cases and up to previous year in Torch and in TensorFlow, they used zero initialization for the biases, and that's okay, since the bias only models this very shift of our value, and since it's like each, let it be, output neuron has its own bias, it will not take us to the situation when they change in the same way as we did as we could observe for constant parameters. So this is just a function for us for like compatibility to init our weights. If you want to init the weights in your layer, use this. This must be a callable function for initialization. Here you should provide either the weight or the bias of your layer. Okay, so let's also define two nice functions. So the first one, train pipeline. What we'll do is we'll just using our train dataset, eval dataset, we will see the performance of this init function. So how the performance changes depending on the initialization function. By the way, for better results and to make them reliable, let's increase the number of epochs. Let them be like 10 epochs, for instance. Need to relaunch this one, and way it was defined, this one as well. Okay, going back to our initialization. What it will do, it will simply, like, we provide for our function the method for initialization. We make a function with lambda x, which will apply like this our init weights. And then the, like, again, the most interesting syntax thing, how to apply this to the whole model. So we use this function to apply to one layer, but if we want to apply it to the whole model, the method apply of the model sequential will do the following thing. It will return each of the modules iteratively, and this function will be applied to each of the modules of this very sequential. So this function will be applied to each of the model of our architecture, to linear, ReLU, linear, batch norm, ReLU, dropout, linear. Here no parameters, here no parameters, here no parameters. Here they will be, interestingly, they will be initialized as usually, but even if, okay, let's do it this way. Let's incorporate the batch norm here so that we'll initialize the weights for it as well. Okay. And it will simply return as a trainer, and then to get the eval loss to see how well or how bad our model initialized with such weights performs on the data set, we will call this function. It will, what it do, it will just see at the log history and return the last eval loss. Okay, so the first method is initializing with zeros. Let's see what it returns. Oops. Pardon. We can see that the RMSE is not changing almost at all, right? So it was definitely not the best way for initializing. But now let's see some interesting things, how to take the model, how to inspect its parameters after using the trainer for fitting the model. So the model is stored in this attribute trainer.model. We can see our model here. And if we want to inspect the values of our weights, so first of all, that's the sequential, right? That's the only module our model consists of. And when we want to take any model from the sequential, you can see they have their own numbers. So here, instead of using dots, we'll need to use the getItem method, which is taking the square brackets. Here, we take the zeroth model from our sequential architecture. Right here is our linear layer. And let's see at its weight. We can see that it only consisted of zeros and it did not change at all. That's it. By the way, I'm sorry. Let me remove this very thing so that I'm sure it's does not influence our experiments. Okay, so again, trainer, model, sequential, zeroth module, and the weight. Yeah, it only consists of zeros. It cannot fit, so due to the initialization. Okay, moving forward. And now let's initialize everything with ones. Calling absolutely the same, we can see that on the first epoch, it tried to change a bit, but after this, it again converged to some bad values, which is not what we wanted, right? So again, let's inspect the weights. And this is what I told about during the lecture. So we can see that we have absolutely the same parameters. This vector, this vector, this vector, and they are absolutely the same. So instead of using 1, 2, 3, 4, 5, 6 output neurons, we could use just one, since they serve absolutely the same purpose. They have absolutely the same values. That's it. So that's the problem with constant initialization of weights. Okay, so we can see that too small. As I told in the lecture, when we initialize from some distribution but without tuning the standard deviation, too large will lead to exploding gradients with some very large values, and too small standard deviation will lead to vanishing gradients problem. It will be very close to this very image. So let's first use the standard normal distribution, one of the most popular ones. Let's train our model. So we can see that the RMSE indeed decreases. Probably if we increase the number of epochs, it would decrease even more. But again, we can see that after several throughout the last several epochs, it was almost plateauing. If we return the weights from the first layer, we can see that now they are different since we did not use the constant values for initialization. But again, the quality is 41 RMSE, while we had significantly lower values for when training with predefined in-torch initialization schemes. The same for standard uniform distribution, like it can provide decent values like here. At least it will not end up like we saw with constant initialization, but again, when increasing number of epochs. Okay, let's remember this very value. This was as we initialized from standard uniform one. And now the modern initialization schemes, first of all, the Javier or Glorot or Hare normal distribution. Okay, and we find up like this is the best value, 25 and 90, while we had like this here. So tuning the scale already, we can see the improvement in the results by almost how much, 15 or like this percent. The next one is the Javier uniform distribution, right? So everything the same. And we can see again the decrease comparing to results which we had with constant value. It was here, right? So here we had 29. Here we have again 25 and 4. That's it. And interestingly, again, we will not make any conclusions based on these results since the data set is too small, the architecture is too simple. But for uniform distribution, it converged a bit faster than for normal distribution. And that's the observation which the authors here and the others made in their article. But our architecture has the ReLU activation function instead of sigmoid or hyperbolic tangent, for which these Javier, Glorot, Hare initialization schemes were initially suggested. So since we're using the ReLU, let's use the K-mean normal distribution or the K-mean uniform distribution, which was suggested specially for ReLU and its modifications. Well, interestingly, that for now it does not provide better results, although these ones are much better than we observed for random random initialization with unseen. Huh?
We tried several times because it can change from time to time, right?
I don't think so, because we fixed the seed in our model, in model init function, and we fixed the seed for trainer. So yeah, surely if we
it might be a little bit different.
yeah, of course. So the main, it will differ both. If we change the seed when initializing the model, it will lead to different initialization, and if we change the seed for trainer, because it will lead us to like different batches on which it will be trained. The last one, the K-mean uniform, which is now used in Torch, but in Torch again of 3 instead of 3, we use 1. And the results, interestingly, they are worse than we saw for the previous initialization schemes, but again, they are better than any initialization with untuned value for the standard deviation. And here is just a small plot which compares all the models throughout the epochs. What just the results underpin our ideas, our claims that ones is not good, zeros, I cannot see the zeros here. I'm not sure whether it was plotted or not here, but we remember it also had very large values for the loss. The normal with untuned, it tries to converge, but not so well. The uniform untuned also, it tries, but does not succeed as the other 4 methods, and they all like the four methods which we saw, they provide similar results for this. Okay, so if no questions here, right? Let's do, we have 35 minutes more, and let's write the algorithm for permutation importance calculation. So what we need to do, the input for the algorithm was the pre-trained model 1, the training data 2, the input features 2, the target labels 3, and the loss function 4. Okay, let's define these 4 parameters and write a function which would depend on these very values and output the feature importances for our data set. What we can do later is we can calculate the feature importance using the linear methods, just fitting a linear regression, and compare the results for our algorithm, whether they will coincide or they will not. Okay, so as for the trained model, we can use, let's use, like, I guess this method provided us with the best RMSE on the evil set. Let's relaunch one time this cell. Okay, we get this. So the trained model, again, we can just take from the trainer model. Train data, let it be our not trained data, but features. Let's call it X. And X will be just the features from our training data set. By the way, at the beginning of the class, we saw this class data set for if we do not want to write our own one. Let's see how it looks like. Just small overview of this. So it shows us the features, num columns. If we want to select several instances and still have it in a dataset format. So if we want just to make a slice of our dataset, the method select, where we need to provide the indices of the observations which we need to query. So let it be like we want to take the first 10 observations. We provide here range 2, and voila, we have our data set with 10 values. If we want to take the whole column, like we want to take all the features for now, we want to take all the features from this data set, we simply use it as a dictionary, and it provides us all the values. If we want to query several values from our data set, but we want to have them returned in a dictionary format. If we want to have the dictionary where the keys are the features from our data set and the values are the corresponding values, we simply, instead of calling method select, we use the get item method. For instance, we want again to take the first 10 elements. What it'll do, it will return a dictionary with 2 keys, with X and Y, where X contains all the features, Y contains all the labels. I guess that's everything what you need to know about the data sets. Yeah, they can be easily initialized from your data. Yeah, I would not say that anything important is here. Yeah, so that's it. Okay, we want to have the features for our algorithm, and this will be exactly train data set querying the key X corresponding to features. Labels, we will use, I guess the another column was called labels. Yes, exactly. So we'll use our labels. Okay. And the last thing which we need, yeah, by the way, they will return all of them as the lists, since they store the data in such a format. So we want to make them NumPy arrays. Let's do it straight away. And we also need the function to calculate, to assess which one is better. Yeah, the loss function. So let's write it here, MSE. I guess it was already written, but it does not take much time to write this function once again. So we simply need to return X minus Y squared and taking the mean of the results, since we want to average throughout our observations. That's it. Okay, we have our features, we have target, we have everything for the algorithm. Let's write it straight away. So permutation feature importance. Again, it accepts the model, the X, the labels, and the MSE. If probably most of you know, but anyway, if you want for like people who will read your code or who will use your code, if you want them to shed more light on which type should each of the parameters be, for instance, for our case, X should be a numpy array, and we want to specify for the user that you should better provide numpy arrays. Probably you can provide some other structures, but we do not guarantee that they will the function will not return an error. We can specify it right here. So we'll say that X must be numpy and D array, labels must be numpy D array. This one will be callable. Probably there is some predefined class from typing, but I'm not sure. Okay. So what we need to do? First of all, we need to calculate the original error of our model on the on our data. So let's do it. Let's recall briefly how we can evaluate our model. We can either use forward method, and call our model straight away, but instead probably it will be a bit easier for us if we use again some predefined methods for this. So what we need to do, or we can omit this step. For now, let's omit this step. I guess the batch size is too small, that we have too few observations that they can all compound one big batch. So if we do it like here, 1 second, I'm sorry. If we make it a torch tensor on our CUDA, that's okay, it works, and the size of the batch for now does not matter. Okay, so let's do it straight away. So the output of the whole on corrected data, right, without permutation, is simply calling our model for this X and reshaping it not to have them in 2D format. Right, so this will be just a vector of observations. Observation I corresponds to the output of the model for the vector of features I. The error array, let's call it this way, is applying the function, the loss function, for our values and for the true values. That's it. Okay, so let's validate these two steps. Let's assure that they will not return us an error anywhere. By the way, it was not great to call it MSC straight away. Let's call it error func here. I guess everything is okay. We need to make them torch tensors, the first step, both of them, or probably only one of them. X is torch tensor. And another important notion here, that we already saw that the model can be trained either on CPU or on CUDA, depending on whether you have this equipment or not. And the data which you provide to the model, it also must be placed on the same device. So it's it can be done very, very simple by simply calling this very method too. Just do not forget to do this, because if you forget, sometimes you may find out that you will get some very strange errors, and it will take you some time to validate them. Okay, so that's the first step which we need to do. Make it a torch tensor and place it to model. Our model does not have attribute device. Okay, let's use our hyperparameter from notebook. That's it. Yes, and again, if we have our model on device, surely the output will also be placed on the same device. Since our labels is just NumPy array, it will not be correct to compare NumPy array with torch tensor on CUDA device. So after calling the model, we need to place it to CPU and make it a NumPy tensor. I guess this syntax is more universal. So sometimes you need to detach, sometimes not. If you do this, it will not take much time. It will take some milliseconds, probably. Okay, so these lines work. For now, I guess that's okay. That's our error, our MSE. And let's copy this part and incorporate into our function. And again here. Okay, so we have the original error. 1 second, I need to recharge my computer. And for now, what we'll need to do, we'll need to take each of the features, permute the values in the column of this feature, and calculate the error. Calculate the error and then subtract the original error from this to have an estimation of the quality of this feature. Okay, so for feature in X, let it be for I feature and enumerate X. You're acquainted with this structure, right? No new code. Okay, so what we need to do, we first need to make a copy of our tensor, and the best way to make the copy to be assured that you will not override this is to import the deep copy function from copy library. So X permuted is X, and now what we need to do, we need to let's make another parameter called seed, and before it's just for you to have the same results as me, so that you can obtain absolutely the same feature importances. We fix the seeds. Since this is a good error of mine, since this is a torch tensor, we also need to fix the tensor for okay, never mind, I'm sorry. We make the copy of our tensor. Let it be, I do not want to make it tensor here. The easiest way is just to put it firstly on CPU, I guess this one. Okay, so now we need to permute the values of this feature. Okay, let it be this way. Let's do the following thing. There is a method NumPy random permute if memory serves, or NumPy just NumPy permute. 1 second. NumPy shuffle, sure. NumPy random shuffle. But to make it applicable to our case, we first need to transform this very X to NumPy format so that we can shuffle this. So we transform our feature to NumPy, CPU, NumPy, and shuffle its values. So yes, it's better done like this. I shuffle the values, and this function, it modifies the values in our NumPy array so that now the values are randomly permuted. What we need to do now is we need to change the value of this column. First of all, yes, I'll put this on CPU. And now the ith value of our feature. I see, it was not the best iteration. So will be equal to our new permuted feature. Yeah, I made an error here as well. So instead of we need to do it like this, because if we set it like X, it will iterate through rows, and we need to iterate through columns, right? Through features. So that's how we do it. we assign the results, we move this again back to original device, and then absolutely the same to make the output of the for the permuted data. We put it to CPU, we calculate the error, error output permuted, and the importance of the feature high importance. Yeah, thank you. Error from let it be minus error a week. And let's create some list for storing these very values. Please let it be. Please append importance. Yeah, I do not guarantee that I did not make any mistakes, but we'll probably validate them easy. Okay, and in addition, we can also add the Tsvigun wrapper here to see our progress, and we'll return the feature importances. We can also return the NumPy array so that it will be easier to work with it in the future. Okay, our function is set, and now we need to provide model, X, labels, and MSE. Model, X, labels, and our function. Let's see. Yeah, that's the problem. It says that we need to transform it to tensor as well. Okay, everything done. Let's inspect the values. Here are the values. Interestingly, that only one negative value. So it means that this feature is probably useless, since when excluding it, we get a better quality, but the majority of them are surely useful. Let's have them argsort, call the argsort method, argsort method for inspecting which features are the most valuable, 33, 34. Okay, now we'll do a similar thing. Let's import the linear regression from sklearn. Linear model, import linear regression. If you remember last time, we saw that on this data set, the regularization did not improve the performance. So we can use the classic the linear regression class for it. Oops. Fit. We have our X and we have our X and labels. Yeah, only X should be transformed back to NumPy array. CPU detach NumPy. Okay, our model is fitted. We can see this square. And now an important thing here is that we should not use the argsort. Yeah, and we should not have used argsort here. We need to first take the module of these values and then argsort, because like, oh, no, I'm sorry. Never mind. Okay, so we have the coefficients. Yeah, but coefficients and feature importances which we get through our algorithm are slightly different. So as for features, a very large negative value may signify that the value is indeed important. Well, for feature importances, which subtracted one loss from another, like the larger the value, the more important the feature is. So to sort them now, we first need to take their absolute values, right? And then we can again call the argsort. So that's it. Yes, surely they do not coincide totally with each other. And what is a bit more interesting, they place different features on the first place. So we can see that feature numbers 33, 34 stand as the most important for our neural network, while for linear regression, they are slightly less important. So here is 33 and 34. Cannot find it. Where it is. It's right here. Again, they like stand together, but they have less importance for linear dependency. And as for like feature 17, for instance, again, it has less importance for neural network and the higher one for linear regression. The same idea holds for the most unimportant features, although we can see feature numbers like 13, 15, which stand in the end in both the lists. So that's the feature importance algorithm, nothing really difficult, but the problem is that especially for small data sets, as we had it now, the permutation could just be the crucial moment, so that this random component that we randomly permute this, it may have had a high influence. So let's make it a bit more stable. Instead, we see that it works extremely fast. It took us less than a second to go through the cycle. So instead of calculating this as a stochastic run for each feature, what we can do is we can have k stochastic runs for each feature. So let it be a hyperparameter, and let's make it something like 10, for instance. For let it be in range k. What we'll now need? We'll now need to average the errors. It's very important that we average the error values, not the outputs of the model. Well, indeed, we can average the output of the model as well, but averaging the error will give us an unbiased estimate for this. So what we will do is we will accumulate, let it call feature errors. We'll accumulate the errors for this feature. Errors append, and as a result, instead of subtracting the like from only one value, we'll subtract from the mean value of our list. Probably this will give us some more precise estimation. Let it be FIS2. Oops. Interesting. Sure, because had it as blah 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 blah. We need to move it here. Yeah. Again, it works extremely fast. And let's see at the order of the feature importances for this very case. You can see that it indeed did not change drastically, yet the order is surely slightly different. So the like feature number 33 is not the most important now, although the overall order seems quite stable. So that's how you can estimate the most important ones, how you can like throw away the unimportant ones. Again, what we spoke about in the lecture, let's do it here as well. The last time we'll call this cell. Let's do it. We only did it on train sample. Let's do it on the evaluation set as well. As we discussed, the features which have high importance on train set and low importance on validation set may cause our model to overfit. So instead of providing X and labels on the training set here, what we can do is we can simply provide X and labels from the eval data set. Let me do it straight away here. So this will be eval this here. And again, the labels will be taken from the eval data set. And let's see the values for the validation set. Oops. We can see that, for instance, feature number 33, it has significantly lower importance on validation set, and probably it can be excluded without like with correct retraining of the model without this feature, we can probably get some better results. But we also can observe that feature 33 is still the most important. That's great. Well, with a brief analysis, I cannot see any other features which are which stand very high here and low here. Probably there are no other probably feature 31, but anyway, feature 33 we can see how drastically its position changed, and probably this one will cause our model to overfit. By the way, the last thing which I want to show now, if memory serves, let's relaunch these very cells. Okay, that's it. That's our X. If I'm not mistaken, features 33 and 34, the ones which were close here and here, they were simply had a dependency close to the linear one. Let's inspect them. No, slightly different values, although yes. Okay, the hypothesis is not true. Okay, so that's the feature importance algorithm which we can use for analyzing which features you should pay attention more or less. Okay, if any questions, let's discuss them. I can see no questions in chat. Okay, so if no questions for now, that's all. Thank you. And an important on the next lecture, we'll have the first test. It will be devoted to theoretical materials, which we covered on the first and on the second lecture. I will also make the announcement in the chat. The questions for preparation, if I do not send it by the weekend, please tag me, I don't know, on Friday, on Wednesday, on Friday, on Saturday. Yeah, there'll be like 1-2 questions from the first lecture, 1-2 questions from the second lecture, something to derive the gradients, something, some questions about dropout, binom, etc. Да, 15-20 минут будет. Да, да. Он будет на лекции, и у нас тесты будут чередоваться, типа в следующий раз на лекции, через один на семинаре, через один на лекции, через один на семинаре и так далее. Все, тогда всем спасибо.